All right, open up your book to section 15-3. We're on page 767 in your book. The title of this section is Series and Partial Sums. Our objective here is, given a series, find a specified partial sum, or find the number of terms if the partial sum is given. Secondly, given sigma notation, or use sigma notation to write partial sums. And third, given a power of a binomial expanded as a binomial series, which actually that third part is what we're going to focus on here in the third part of section 15.3. So what exactly is a binomial series? Well, binomial series is an expansion of a binomial. When you take a binomial and you expand it, that is, you raise it to a power, you don't just take the first term and raise it to that power and add it to the last term raised to that power. There's some middle terms that show up. So for example, if I take a plus b and I raise it to the third power, I end up with a cubed plus 3a squared b plus 3ab squared plus b cubed. If you actually multiplied that out, a plus b times a plus b times a plus b 3 times, multiply it all out, add everything up, you end up with this. That's a binomial series. Now the question is, well, where does that come from? How do I get this guy right here? If I know I'm taking a plus b and raising it to the third power, how do I come up with that? Well, the key there is to probably rewrite this using all the terms and actually writing in the coefficients to help you look for what pattern you're trying to find here. The a cubed is really a coefficient of 1 times a cubed times b to the 0. Of course, anything to the 0 power is 1, so that's why we usually leave that off. The one out front we usually leave off. So that's why it was just a cubed. The second term, 3a squared times b to the first. Now, that's basically the same thing we have above, but we're actually writing the exponent there with a b. The third term there is 3 times a to the first power times b squared. And then finally, 1 times a to the 0, b to the third is the same as b cubed. So now I have each one of these written with a coefficient, with the first term raised to some power and the second term raised to some power. I've got everything written down there in that second form. So let's look at what kind of pattern here, I guess, that develops from this in the more general sense. If I were taking a plus b and raising it to the nth power, how can I use what I see there to help me understand what's going to happen in the general case? Well, the first thing to do is notice how many terms you have there. When I took a plus b and raised it to the third power, I actually ended up with 4 terms. If I had a plus b squared, I'd have 3 terms. A plus b to the fourth power, I'd have 5 terms. Turns out there's always one more term number than the power of n. So n plus 1 terms. The next thing to notice is that the degree of each term is n. When you calculate the degree of a term, you add up all the exponents, by the way. So in that first term, 3 plus 0, that's 3. That's a third degree. The second term there, you have a squared b to the first. 2 plus 1, that's 3. The next term, 1 plus 2, that's 3. And the last one, 0 plus 3, that's 3. All of these have a degree of 3. There's no variation from that. Take a look at what happens with the exponent on a. On a, you begin with a to the nth power, and it decreases all the way down to a to the 0 power. So it's a to the third in the first term, a to the second in the second term, a to the first in the third term, and finally a to the 0 in the last term. So the exponent on a is decreasing. And likewise, check out what's happening with the exponent on b. b starts out with an exponent of 0. That's b to the 0 in the first term, and then b to the first in the second term, so it's increasing. B to the second in the third term, and then finally b to the third in that fourth term. So the exponent on b is increasing from b to the 0 all the way up to b to the nth. The other thing to notice here about the coefficients, there's some symmetry there. Actually, once I know the first two coefficients, I know the last two. Starts out with a 1 and a 3, and then ends with a 3 and a 1. So the coefficients are symmetric. Now, I still need to know how to come up with those coefficients now, and be careful with reading too much into this example. You'd want to have an example with maybe a to the 4th or a to the 5th to help you see what the coefficients might be. But we do need to figure out how do we come up with those coefficients. But the nice thing is once I get halfway through this, I can just reuse that, those coefficients because they just repeat. All right. I guess that's the next question then for us, is how do we figure out what those coefficients are? Well, it turns out there's actually a couple of ways that we can do it, 3 ways that we can do it. The first way that we can do this is by using what's called Pascal's Triangle. That's probably something you've heard of, or I assume you've heard of it. If not, we'll refresh your memory right here. The Pascal's Triangle looks something like this. We usually draw this kind of as an equilateral triangle when we draw this out. But the top row of Pascal's Triangle starts with a 1. The row below that starts with a 1 and a 1. Starts with a 1 and ends with a 1, I should say. The next row, and in fact, every row hereafter is going to begin with a 1 and end with a 1. So I'll start with a 1. But now to figure out what the number is that goes in the middle here, it turns out it's 2, and I get the 2 because of the fact that I can add these two numbers above it, 1 plus 1, to give me that 2. So it begins with a 1, ends with a 1, and has a 2 in the middle. For the third row, or actually this is the 4th row of Pascal's Triangle, starts with a 1. I'll take the 1 plus the 2, which is going to give me a 3. I'll take the 2 plus the 1, which is going to give me a 3. And then, of course, it ends with a 1. And we can continue with this. The next one's going to be 1, 4, 6, 4, and 1. All right, so what's the significance of these numbers? Well, hopefully when we got to this row right here, you went, oh, those numbers look familiar. We just saw those on the previous slide. Those were the coefficients of a plus b to the 3rd power. And those turn out to be the coefficients for any one of these raised to whatever power you're going to want to have. Pascal's Triangle actually gives you those coefficients there. What you have here is this very first row of this are the coefficients of what you'd end up with if you took a plus b and raised it to the 0 power. Anything to the 0 power is just 1. The next row is what happens if you took a plus b and raised it to the 1st power. Well, you end up with the same thing you started with, so that's why the coefficients are 1 and 1. What happens if you squared it? Those you might recognize. If you take and square a binomial, you know you end up with a squared plus 2ab plus b squared. And here are the coefficients of what we ended up with if we took a plus b to the 3rd power, and so forth. So for our example here, now that I know that, if I can remember the first few rows here of Pascal's Triangle, or keep writing some down if I need to, then I can use that to help me quickly come up with what this is equal to. That I know that I'm going to start out with 1 times a to the 3rd power b to the 0. My next coefficient is 3 times a to the 2nd power b to the 1st. My next coefficient is 3 times a to the 1st power b to the 2nd. And finally, 1 times a to the 0 b to the 3rd. Now that's writing everything out. And I would definitely recommend as we start doing some of these problems that you start with that, writing everything out. But eventually you'll get to the point where you're comfortable just kind of leaving out the stuff you don't need. I don't need the 1 and the b to the 0, so I can write this as a cubed. Here I'll write this as 3a squared. I don't need b to the 1st, so I can just say b. Here I can write it as just 3a. I don't need the 1st power written down there, times b squared. And finally, at the end, I don't need the 1. I don't need the a to the 0. This is really just b cubed. And again, that's exactly what we had on the previous slide. So this is one way you can do it. Either know the first few rows here of Pascal's Triangle, or if you need a row that you don't know, you got to start writing it out, which I guess that's the disadvantage. If I wanted to raise this to the 10th power or whatever, some bigger power, I got to write down probably quite a few rows before I'll know exactly what the coefficients are going to be. I probably don't have the first 10 rows of Pascal's Triangle memorized. So what's another way we can do this? Well, The second approach is more of a recursive method. And the recursive method means that you use the current term to help you figure out what the next term is going to be. So you use the current term to find the coefficient for the next term. So here's what you do. To find the coefficient of the next term, you'll take the coefficient of your current term and you'll multiply it by the exponent of your current term. And you'll divide that by the exponent of your current term for b plus 1. Now the book also says you can divide by the term number plus 1, but that's probably not a number you're keeping track of as you do this. So you are writing down the exponents of a and b as you go, so those are easy to come up with, and you're writing down the coefficient as you go. All right, now with a recursive formula, of course, you always have to have a starting point, just like we've talked about with recursive formulas for your arithmetic or geometric sequences. So you do have to know your starting point for this, and I hope that you recognize that you always start out with a coefficient of 1, and you always start out with a to the third power and b to the 0 power. So that's our starting point. All right, so what's the next coefficient? Well, let's use this little technique here. It says take your coefficient, which is 1, multiply it by the exponent of a, which is 3, and divide it by the exponent of b plus 1. That's going to be 0 plus 1. And of course, what's that turn out to be? Well, 1 times 3 divided by is 3, divided by 0 plus 1, that's 1. 3 divided by 1, that's better known as 3, right? So this right here is just equal to 3. All right, let's write down our terms here, our other two factors. It's a squared times b to the first, right? All right, let's find out the next one. Now the next one, we take the coefficient here for this term, which is 3. We multiply it by the exponent of a, which is 2. And we divide it by the exponent of b, which is 1 plus 1. And again, the question is, well, what's that equal to? What's this guy equal to? 3 times 2 is 6, divided by 2 is 3. This turns out to be 3. And again, this is a to the first, b to the second. All right, for the last coefficient, now again, once you get halfway through this, you already know the other coefficients, but let's go ahead and check to see that this still works. But also, you should know when you get to the last one that you always end with 1 as well. You start with 1 and end with 1, so we really shouldn't have to do a calculation here. But let's go ahead and check this out and see if it still works. If I take the coefficient, which is 3, multiply by the exponent of a, which is 1, and divide by the exponent of b, which is 2 plus 1. That's 3 divided by 3. 3 divided by 3 sounds like a value of 1. So we're going to end up with 1 times a to the 0, b to the third. Or if you will, again, as you go through this, you'll probably start writing down all these parts as you go the first few times, but eventually you'll get more and more comfortable with this. So you've got a cubed plus, you'll go 1 times 3 divided by 1, that's 3. A squared times b. And then you go 3 times 2, that's 6, divided by 2, that's 3, times a to the first, b to the second. Actually, you probably won't write a to the first, actually. In fact, I'll go ahead and erase that. And then finally, for the last one, again, once you're halfway through, I hope we don't have to keep doing the recursive formula, but just to see that we get there, you go 3 times the 1 here is 3, divided by 2 plus 1, 3 divided by 3, that's 1, times the b cubed. There we go. So that's the second way you can do it, a recursive formula to help you just go through one term at a time. Now that's nice because I don't have to know the entire Pascal's triangle in order to come up with those coefficients. I can use one term to help me get to the next one. The last method actually uses combinations. This is a technique that we've talked about in the last chapter, actually. We're dealing with combinations when we're calculating probabilities or number of outcomes. But it turns out you can use combinations to come up with these coefficients. Combination of n objects taken r at a time, where r is the exponent of b. So n choose r, that's one way to do it. The other way to do it that we're going to write this is n over r in parentheses like this. That also means a combination. Remember what this means. This is n factorial divided by n minus r factorial times r factorial. That's what this means if you want to write it out as a factorial. Okay, so let's see if we can write this out here then. If I take a plus b to the third power, I can write this as 3 choose 0 times a to the third b to the 0. Again, I'm going to write everything out here as we go, but eventually we'll try to get ourselves to the point where we're more and more comfortable with just writing down the numbers we end up with or we come up with. And then it's 3 choose 1 times a to the second, b to the first. And then it's 3 choose 2, a to the first, b to the second. And finally 3 choose 3, a to the 0, b to the third. What's this turn out to be? Well, 3 choose 0, if you have 3 objects to pick from and you're not going to pick any of them, there's only one way to do that. Don't pick any. So that's 1. B to the 0, that's 1. So this just turns out to be a to the third. 3 choose 1. If you've got 3 objects and you're going to pick one of them, you can either pick the first object. That's one way to do it. You can pick the second object. That's the second way. Or you can pick just the third object. There's 3 ways to do that. 3 choose 1 is 3. A squared b. 3 choose 2, well, that's actually just the opposite of what we did. 3 picking 1 is the same as saying 3 don't pick 2. But anyways, 3 choose 2, you could pick the A and the B, I'll call them. You could pick the A and the C, or you could pick the B and the C. There's 3 ways to make that happen. And finally, 3 choose 3. Well, if you have 3 objects and you got to pick 3 of them, there's only one way to do that. You got to pick all of them. So 3 choose 3 is 1. A to the 0 is 1. This is just b cubed. Now, for some of these combinations, you'll probably have to grab your calculator and let it crunch those numbers for you. That might not be quite so easy to do without a calculator, or at least to try to do it just in your head. But nonetheless, we can use combinations to come up with these coefficients. So you've seen now 3 different ways to come up with those coefficients. Let's try this out. What exactly is our binomial theorem then? The binomial theorem states the following. We're going to write this in terms of a combination. This is kind of the last thing we saw on that previous slide there that illustrates this. But if I've got a plus b and I want to raise it to the nth power, I can write that as a sum of these products here. It's n choose 0 times a to the n, b to the 0, plus n choose 1, a to the n minus 1, b to the first, plus n choose 2, n to the a to the n minus 2, b to the second, and so forth, all the way up to n choose n times a to the 0, b to the n. Or if you want to write that as a summation or a sigma notation, this is what that would look like. It's the sum from r equals 0 to n. It's a combination of n choose r. It's a to the n minus r, b to the r. That's what it would look like as a sigma notation. Now we call this the binomial theorem. It tells us how we can expand a binomial is basically what it is. This, by the way, is also the same property you learned in the last chapter when you're talking about a binomial experiment. If you think about that formula we learned for that, that's the same formula here. Where the A and the B are representing probabilities of either your event occurring or not occurring. And the combination that you have out front is the number of different ways of arranging those outcomes. The binomial theorem is also known as the binomial formula. Sometimes it's referred to that, and sometimes it's called the binomial series, which actually is what the objective called this. So any one of those names is fine to call this. Binomial theorem, binomial formula, binomial series, all the same thing. All right, so let's try using this. Take a look at example 5 here on 774. It says to use the binomial formula, binomial theorem, binomial series, to expand the binomial x minus 2y to the fourth. X minus 2y to the fourth. Right, now one way you could do this is you could write x minus 2y times x minus 2y times x minus 2y times x minus 2y. And then have some fun with foiling all that out. We're going to use the binomial theorem here, the binomial formula, to evaluate this. Now I'm going to write all the terms out here, and I'd suggest again, as you start this, you write all the terms out. As you get more and more comfortable, you can probably leave out some things here, but I'm going to write everything down. The first thing I need to know is my coefficients. So I've got 3 different ways to come up with those coefficients. If I know my Pascal's Triangle well enough for the first few rows, then I'm all set. I can use that recursive formula, or I can use combinations. Now for this problem here, since I'm only raising this to the 4th power, I know that 5th row of Pascal's Triangle looks like this, 1, 4, 6, 4, 1. That's what Pascal's Triangle tells me. So I'm going to use that. But if you don't know that, then you got to use some other technique there to help you come up with that. All right, so let's write this out. So it starts out with a coefficient of 1. I take the first term, which is, actually, I should probably rewrite this actually one way here. Let me do that. I'm going to rewrite this as x, instead of minus, I'm going to write this as x plus the opposite of 2y. That might help us out here when we use this binomial formula. The binomial formula is based on the sum of these two terms, so I want to write it that way. Okay. So we've got the coefficient of 1 to start off with. You take the first term, which is x, and you raise it to the 4th power. You take the second term, which is the negative 2y, which is why I wanted to rewrite it this way, so we realize we got to grab the negative along with this, raise to the 0 power. We add to that the coefficient from up above there was 4. It's going to be times x to the 3rd power and the negative 2y raised to the 1st power. The next coefficient is 6 times 6 squared, and then a negative 2y raised to the 2nd power. The next coefficient is 4 times x to the 1st power, and then times the negative 2y raised to the 3rd power. And finally, it's 1 times x to the 0 times your negative 2y, I'm going to try to squeeze that in here, raised to the 4th power. Negative 2. All right, now let's simplify this. Again, if it's easier for you to write them all out first and then simplify, then do that. As you get more and more comfortable, you'll probably be able to leave some things out. The 1 and the negative 2y to the 0, of course, those are 1, so I can just write this as x to the 4th. The next term here, now be careful with the sign here. You've got a negative 2y that you're raising to the 1st power. So that's really a negative 2 times 4th. This is going to be a minus 8. Realize that this is going to alternate signs. If you're subtracting, which is what we had here, x minus 2y, you're going to end up alternating signs as you go through there. So you've got x cubed, and then it's y to the 1st. I'm just going to write it as y. The next one, we've got a negative 2y, and we're squaring that, so that's 4 times 6 is 24 x squared, and it's a y squared. Next one I know is going to be negative because we're alternating signs here, but you can check that out. If you take negative 2 and cube it, that's a negative 8. Times 4 is a negative 32, and it's going to be x times y to the 3rd. And the last one there, you've got a negative 2 to the 4th power. That's actually 16. So I'm going to have 16 y to the 4th. There we go. I just expanded that binomial. I did it actually in a couple steps, but I probably could have done that in one step as I get better and better at this. Much, much faster than trying to write out these 4 factors and multiply that out using a foiling technique or a lattice, whatever technique you use to expand a binomial. Definitely much faster this way. All right, let's take a look at one last example here. Example 6 on the same page. This says to find the 8th term of the binomial expansion 3 minus 2x to the 12th. 3 minus 2x to the 12th. And they don't want the whole expansion, they just want the 8th term. Now there's a couple of different ways they could word this problem, so I want to write it both ways here so you can see that. One way to do it is like they said, find the 8th term. All right. The other way they could do it is by indicating the exponent on whatever your variable is here. So I've only got an x in this one. On the previous one I had an x and a y, so they could have written in terms of x and y. But here they'd have to write it just in terms of x. The very first term of this, if I expand it, is going to be raising this to the 0 power. In other words, the exponent on the x is 0 for the first term. The exponent on the x would be a 1 for the second term, a 2 for the third term, and so forth. So the other way they could state this is they could have said, or the x to the 7th term is another way of stating the same thing here. I'm just pointing out both ways that you could see this written. Some problems will be asking for the 8th term. Some problems will be asking for the x to the 7th term. Asking you for the exact same thing is the key to recognize here. All right, So how do I go about calculating that 8th term, or the x to the 7th term? Well, again, with this being subtraction here, let's rewrite this as 3 plus the opposite of 2x to the 12th power, just so I get the negative sign along with this. Again, that's something that you probably might want to do here initially, but as you get better and better at this, you can probably leave off that step there of rewriting it as addition. And now, if I want the x to the 7th term, that means that I'm going to be looking for raising this second part here to the 7th power. So if I want to write that as a combination, again, this is raised to the 12th power, so it's, how do I want to write this? I'll call this the 8th term. All right, the 8th term, it's going to have a combination, and then it's going to have 3 raised to some power, and it's going to have a negative 2x raised to some power. That's the form of the answer I'm looking for. The question is, what's the combination that goes out front, and what are these two exponents I got to put on these two guys? So again, my power here is the 12th power, so that's that's the number of objects I'm picking from for my combination. And since I'm looking for the 8th term, which means I'm raising this to the 7th power here, that means it's 12 choose 7. Remember that the r value here is what you're raising the second term to. That's why sometimes knowing this connection here, to go back and forth between the two if you need to, will help you out. So it's 12 choose 7, which makes the rest of this pretty easy. If that's 12 choose 7, then that means that you've got 3 raised to the, I'm going to go ahead and write it as, 12 minus 7 power, just so you can actually see how I come up with that, but that's how we come up with it, the difference of those two. And then it's x, or the negative 2x raised to the 7th power. All right, 12 choose 7, well, that's going to be a big number. I'm not going to do that without my calculator, but we'll grab that in a second and check that. So 12 choose 7, and then this is actually 3 to the 5th power. I'm going to go ahead and write it that way, actually. And I think I'm going to let my calculator help me out with that. 3 to the 4th power is 81, so probably could do that without a calculator, but I'm going to let my calculator help us out. And then we've got a negative 2 to the 7th power and an x to the 7th power. So I'm going to write this, split this up as negative 2 to the 7th power, and then I've got my x to the 7th at the end. All right, so this stuff out front here is some number. I want to find out what is this number right here. That's what I want to do. And then I can write this as some number times x to the 7th. So let's grab our calculator and figure out what that is equal to. All right, so on our calculator, let's just do this calculation. We're just going to do it right from the home screen here. So we have 12. Under your math menu, you can go grab combination. 12 choose 7. Again, this is the notation you have to use on your calculator to do this. But we'll use that parenthesis notation when we're doing a binomial expansion like this. We won't use the NCR notation. And then it was, what, the 3 to the 5th power? I guess I'll put it in parentheses. I don't really have to do that, but we'll do it that way. And then we have the negative 2 raised to the 7th power. Now be careful with that one. You want to take the negative 2 and raise that to the 7th power. In this case, you'd end up with the same thing both ways, but if it was raising it to an even power, leaving out the parentheses would cause an error here. You'd get a negative number, and it's not supposed to be negative. So make sure you do the right order of operations there. So there we go. That value right there is the number we're looking for. That is a big number. Let me just grab a picture of that. All right. So what do we have here? We've got, how big is that number? 24,634,368, looks like. So negative 24,634,368. 368. And it's x to the 7th is what we have. There you go. That would be a lot of work to do if I was just trying to find out what that term was, just using algebra techniques, but using the binomial theorem, much, much better way to solve this problem. All right, that right there is the end of the third part here of section 15.3.